Okay, guys, welcome. Today we're going to continue our discussion of inverse functions, but we're going to talk about it now in a more using a graphical approach. So what I would like to be able to do in this section is let's try and be able to sketch a graph of an inverse function from the original. We'll talk also about the horizontal line test, which you can use to determine if a function has an inverse. And then we'll talk about how we can tell if a function is increasing versus when it's decreasing. And then we'll also talk about how to obtain an inverse function for a function that's given by a table. Okay, now in the last video, we discussed the example where we have f of x is x squared, and our domain was 0 to 2, right? And we eventually found that the inverse was the square root function, right? Or we said that the square root, I believe in the last video we said square root of y. All right. Now, of course, on 0 to 2, this will work. All right. So I want to show you what the inverse sort of looks like in terms of a graph. Now, on 0 to 2, here's what 1, 2, 3, 4. Here's what our original f looks like, right? So we have, when we plug in 0, we get 0. When we plug in 1, 1 squared is 1. When we plug in 2, 2 squared is 4. So our original function looks something like this. And I guess since it's ending at 2, I should really put a dot there. All right. Now, what does the inverse function look like? Well, the inverse is the square root of x, and we can plot a couple points for that. When you plug in 0, you get 0. When you plug in 1, you get 1. But when you plug in 2, you get square root of 2, which probably we don't know off the top of our head, right? For square root of 3, we don't know that either, but square root of 4 we do know is 2, right? So you're going to get sort of something like this. I should stop it there. So it should have something like this. All right. Now, if you look, the graphs sort of look similar, right? And it turns out that if you flip it over this diagonal line, assuming that I've drawn it a little better, that you should get the same thing, right? And that's maybe one thing that you'll notice that we're going to sort of build up to in just a second here. Okay, so how can we look at a one-to-one function and its inverse on a graph? Well, we know that a point is on the graph of a one-to-one function if the opposite point, b comma a, is on its inverse, right? And if we look at our example up here, the origin is not interesting, right? Because 0, 0, if you flip that, is the same thing. 1, 1 is also not interesting because if you flip that, you get the same thing. But if you look at 2 comma 4, which is on the original, you'll notice that 4 comma 2 is on the square root function, right? So that's an interesting property to note. All right, and then next comes this idea that a function and its inverse are symmetric about the line y equals x, right? So that's an important fact that we sort of just discussed here. And of course, you can get what that second bullet really means is that you can really get one from the other by flipping it across the line y equals x, right? So we'll look at an example of that. Okay, I think what I will do instead of this example is let's look at maybe a more enlightening example. So let's look at something where we have the domain as -2 to 2, and our function f is x to the third. I think that would be a good one to look at. All right, so let's sketch the graphs of both of these. So of course, to get both of these, we'll need the inverse, right? So the inverse of this, well, we'll get that by place f of x with y. Okay, And then I would need to solve for y, so I'm going to need a cube root of y is equal to x. So then my inverse, oh, I forgot to switch. So this should be x and this should be y. All right, but I'm going to get the f inverse of x is cube root of x. All right, but it actually turns out that if we just had f of x is x to the third, we don't even really need to solve for it. All right, let's graph f. And we'll do -2, -1, 0, 1, and 2. Right? Well, if I plug in -2, -2 times -2 times -2 is a -8. If I plug in -1, you'll get a -1 to come out. 0 will give you 0, 1 will give you 1, and 2 will give you 8. So we can draw f by using these points here. So we need to go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have that f, -2, -8 is here. -1, -1 is here. 0, 1, 1, and 2, 8. So we have that our f looks something like this. All right. And again, what are these points? Well, this is 2, 8. This is 1, 1. This is 0, 0. This is -1, -1. And this is -2, -8. Well, then what does that tell us about the inverse? Well, the inverse has the opposite of these points here, right? So the inverse has, instead of -2, -8, it's -8, -2. The three middle ones will stay the same, -1, -1, 0, 0, 1, 1. And then the last one would be 8, 2. Right? So if I add some more hatches, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8. We'll try and go not too far off script. But the inverse, so -8, -2, is going to put me somewhere way over here. -1, -1 will put me here. Oops. 0, 0 here, 1, 1 here. And then 8, 2 will be up here. All right, so you're going to get something that sort of looks like this. I don't know why it keeps doing that. All right, so we get something that looks sort of like that. And of course, if you were to draw that line, y equals x, you get that symmetry along that dashed line. All right, so that's the idea behind the inverse. Okay, so let's look at this graph here. So we want to know, is this function one-to-one? All right, now again, what does it mean to be one-to-one? It means that for each x value, for each y value in the range, only one x value maps to that y value. Right, and unfortunately, there's a problem. I think just about with every point that's on here. Right, so if you look, for example, when y equals 1, well, you have this x value that corresponds to it. You have this x value that corresponds to it. And you have this x value that corresponds to it. All right, so of course, if you look at y equal 1, there are 3 x values. So what's the conclusion? The conclusion is that this is not one-to-one. Because you would need y equals 1 to only have one x value that maps to it. All right, and of course here you have more than one. So what this essentially means, and I mentioned this in a previous video, is that you can modify the vertical line test to sort of make this work for you now, right? So a function is one-to-one if every horizontal line intersects the graph at most one point, right? So in this previous example, you can see that that horizontal line where y equals 1 obviously doesn't hit only one time, so that would not be a one-to-one function. All right. Now, if we look at this function here, would this be one-to-one? Well, yeah, sure, because any horizontal line that I draw only hits one time. So any horizontal line hits only one time. So f is one-to-one. All right. And it's that simple. Now, of course, there are functions. I don't know if the book has an example here. No. So I want to say a note. Look at something like this. Let's make that a little better. So let's say if I had something like this. Now this passes the horizontal line test. But of course, what does it fail? It fails the vertical line test. So it's not even a function. Right? So a one-to-one function is a subset of the set of functions, right? So you can't have a one-to-one non-function, right? So in order for it to be a one-to-one function, you can essentially think of it as it has to pass both the horizontal and vertical line tests, right? So that's something to be aware of. Okay, so now we can talk about what we mean by increasing and decreasing functions by looking at a graph. And we say that, of course, a function is increasing if you have that f of a is less than f of b when a is less than b. All right, what does this mean in English? It means as you move from left to right, the graph goes up. Right, and of course you can define decreasing a similar way if f of a is greater than f of b when a is less than b. But again, in English, this just means as you move left to right, now you're decreasing so the graph goes down. All right, so let's look at a couple of examples of that. Okay, so in part A, we want to find the largest interval on which f is increasing. I typically find that the easiest thing to do with these problems is to sort of separate it, right, into each sort of group. So it looks like if you follow the graph from left to right, it looks like you're going down until you get to about here, right? And this section is all decreasing because it's going from, as you move from left to right, the graph goes down in that area. And then it looks like it's increasing until we get to about 5, right? And of course here it's increasing. And then of course here it's decreasing. All right, so in part A, we want to find the largest interval on which f is increasing. Well, it looks like we're increasing from 1 until we get to 5. All right, and that's the only spot where we increase, so it can be the largest, sure, fine. In part B, we want to find the largest interval in which f is decreasing, and it looks like I'm decreasing from -1 to 1 and also from 5 to 6. So the bigger interval there is -1 to 1 is where we are decreasing. Right, and also in part C, they don't want to leave the other part out. Find the largest interval containing 6 on which f is decreasing. So of course that gives us from 5 to 6. We're also decreasing. Right, so that's how we sort of can determine if a graph is increasing or decreasing. Right, let's see, did I accidentally copy? I think I copied a slide by accident here, right? I guess the only thing that we have here is that we now are specifying for an entire domain, right? So an increasing function is the entire time, right? If you're looking at A and B are in the domain, this is the entire time. Time is increasing, right? And of course, entire time decreasing for a decreasing function. Right. So, for example, the graph of f is a decreasing function because it's decreasing the entire time. Right? In part B, even though you sort of slow up right here, it's still on the way up. So f is, so this is g. So g is increasing, an increasing function. Right? And then finally, in part C, you do both, right? Because here you're decreasing, but here you're increasing. So h is neither. Right? Because you do both increasing and decreasing in h. Okay. Now this allows us to say a couple of nice things. This allows us to say that if you have an increasing function, it's 1-to-1. If you have a decreasing function, it's also 1-to-1, right? As soon as you do both, you can't be 1-to-1 anymore, right? And other nice things are that the inverse of an increasing function is also increasing, and the inverse of a decreasing function is also decreasing, right? So that's one nice thing that we could say. Okay. Now, finally, let's look at how we can talk about functions and inverses with a table. All right, so here we have f is this function displayed by this table. In part A, we want to know what is the range of f. Well, the range of f is the y values. So it's just a set of 4 numbers, and I'll put them in the curly brackets like the domain is up here. Our range of this is 3, -5, 6, and 1. If you want to order it from least to greatest, that's fine too, but it's not wrong to list it this way. Now we want to explain why is f 1-to-1. Well, look at our y values. Do any y values have 2 different x values? And of course the answer is no. No, so it's 1-to-1. All right, and then finally, here's the easy part. What is the table for f inverse? That's just switching the columns, right? So now for f inverse, I need to take my left side of the column, which was 3, -5, 6, and 1, make that my new left column. And then I need to make the right column, still matching the same numbers together, my new right column. So this is 3 square root of 2, -5 goes with 8, and then 6 goes with 17, and 1 goes with 18. All right, so that's that one. Right? So of course you can summarize this by saying that you have a 1-to-1 function in a table, if there's no repetitions in the second column, right? And of course, how do you find the inverse? You switch the columns. All right, so that's sort of a table approach to those functions. All right, so that wraps up this video on graphical approaches to inverse functions. So I hope you enjoyed, and I will see you next time.